Our group today is going to be talking about nuclear energy. So, let us first start with the world energy demand and its impact on society and the environment. So, the global electricity demand has increased by 4% in 2018. This is nearly twice as fast as the overall energy demand, and it is now at its fastest pace since 2010. Renewables and nuclear power met the majority of the growth in demand, but however, the generation from coal and gas-fired power plants increased considerably, driving up the carbon dioxide emissions from the sector by 2.5%. As we all know, the demand for technology is ever so increasing, and as far as we see it, the more the demand for technology increases, the energy demand can only be expected to increase and not decrease. So energy has both positive and negative impacts on societies. Access to abundant, affordable, secure, safe, and clean energy is very beneficial for humans, but the energy extraction itself, transportation, and use can have negative consequences to the health, environment, and economics of a society. Moreover, relying on imported energy can create vulnerabilities to a nation's security. The impact of energy decisions are not always equal for all people. Poor or marginalized societies are more likely to suffer the negative consequences of an energy decision because they have a reduced capacity for adaptation, and they may also lack negotiating power compared to wealthier societies. Therefore, vulnerable populations can benefit greatly from improvements in energy accessibility, safety, or affordability. And at the same time, these vulnerable populations uh, can face great disadvantages if anything were to go wrong in these decisions. So now let us look at the environmental impacts of energy. The environmental impacts of energy use on humans and the planet can happen anywhere during the life cycle of the energy source. The impacts begins with the extraction of the resource. They continue with the processing, purification or manufacture of the source, its transportation to place of of energy generation, and ends with the disposal of waste generated during use. Extraction of fossil fuels can be used as a case study because its use has a significant impact on the environment. As we mine deeper into mountains, farther out at sea, or farther into pristine habitats, we risk damaging fragile environments, and the results of accidents or natural disasters during extraction processes can be utterly devastating. Fossil fuels are often located far from where they are utilized, so they need to be transported by pipeline, tankers, rail, or trucks. These all present the potential for accidents, leakages, and spills. When transported by rail or truck, energy must be expended and pollutants are generated. Let us now move on to the energy electricity generators from fossil fuel sources. So there are two main types, which are the steam engine and the diesel engine. So in a steam turbine power plant, fuel is burned in a furnace and the hot gases flow through a boiler. Water is converted to steam in the boiler. Additional heating stages may be included to superheat the steam. The hot steam is sent through controlling valves to a turbine. As the steam expands and cools, its energy is transferred to the turbine blades, which turns a generator. The spent steam has very low pressure and energy content. This water vapor is fed through a condenser, which removes heat from the steam. The condensed water is then pumped into the boiler to repeat the cycle. Emissions from the boiler include carbon dioxide, sulfur oxide, and in the case of coal, fly ash from non-combustible substances in the fuel. Waste heat from the condenser is transferred either to the air or sometimes to a cooling pond, lake, or river. Now for the diesel engine. The diesel engine generator sets are often used for prime power in communities not connected to a widespread power grid. Emergency power systems may use reciprocating internal combustion engines operated by fuel oil or natural gas. Standby generators may serve as an emergency power for a factory or data center, or may also be operated in a parallel with the local utility system to reduce peak power demand charge from the utility. Diesel engines can produce strong torque at relatively low rotational speeds, which is generally desirable when driving an alternator, but diesel fuel in long-term storage can be subject to problems resulting from water accumulation and chemical decomposition. Chemical decomposition. Rarely, used generator sets may correspondingly be installed as natural gas or LPG to minimize the fuel system maintenance requirements. Spark ignition internal combustion engines operating on gasoline, propane, or LPG are commonly used as portable temporary power sources for construction work, emergency power, or recreational uses. Reciprocating external combustion engines, such as the Stirling engine, can be run on a variety of fossil fuels as well as renewable fuels or industrial waste heat. Installations of Stirling engines for power production are relatively uncommon. Historically, the first central stations used reciprocating steam engines to drive generators. As the size of the electrical load to be served grew, reciprocating units became too large and cumbersome to install economically. The steam turbine rapidly displaced all reciprocating engines in central station services.
Energy conversions and thermal physics in a steam generator. A steam turbine-driven generator, sometimes known as generators, which you can see at the side right of the side, can be best explained by understanding a steam turbine and a generator separately. A steam turbine is a steam-driven driver. Water is heated at an extremely high temperature to convert it into steam. Energy is created by highly pressurized steam is converted to mechanical energy which rotates the blade in the steam turbine. And a generator is best described as a machine by which mechanical energy is transformed into electrical energy. The coiled wires used in a generator spin inside a magnetic field which causes an electric current to flow through the wire. When a steam turbine is connected to a generator, it produces electricity and is known as a steam turbine-driven generator. The auxiliary systems built in them make them work safely and with greater efficiency. Steam turbine-driven generators are commonly used in nuclear. They are also used extensively in cement, sugar, steel, papers, chemicals, and other industries. Steam turbine-driven generators can range widely in size. They rarely exceed about 1,500 megawatts on the top end and are used on a small scale as well, down to about 500 kW on the low end. Steam turbine-driven generators are generally high-speed machines. Most of the electric power in the world is produced by a steam turbine-driven power plants. In the United States alone, around 85% of the electricity is produced using steam turbine generators.
Explanation on the workings of nuclear energy. The process by which nuclear energy is produced. Firstly, splitting of atoms. Uranium atoms are placed in a reactor core. A chain reaction is produced inside the core, which splits the atoms. Uranium is an unstable element. By splitting it, the metal becomes a different stable element. Heat and radiation are the byproducts produced by this process. Secondly, absorption. Control rods are used to absorb the free floating neutrons released during the fission process. Boron released into the cooling water helps to absorb these as well. This is to contain radiation and keep the reactor cool and safe. Thirdly, heat. The heat and radiation produced by the fusion begins to heat the water or the coolant that surrounds the reactor. This water serves two purposes. It keeps the reactor from becoming overheated while carrying away the heat and steam, which will power the turbines. Fourthly, water and piping. Water is continuously flowing through and around the reactor and serves as a coolant. Two sets of pipes carry this coolant in and out of the chamber. The primary pipes supply cold, fresh water to the tank, while the secondary pipes carry away the hot water and steam to the turbines. Once the secondary pipes have carried the water out of this pressurized chamber, which prevents the water from boiling, the heated water is able to boil into steam and power the turbines. The two systems of pipes never interact with one another in order to keep the temperature in the chamber perfectly balanced and to control the amount of heat and steam produced by the reactor.
Okay, an advantage of nuclear energy is that it is cheap to produce, like more cheaper than coal, oil, and natural gas plants. So it was proven that it was proven by the World Nuclear Association that less uranium can be used to produce the exact same amount of energy that is produced by coal, oil, and natural gas. And that also that shows that the cost is lower to produce them by nuclear energy. And then another thing is, but disadvantage is that nuclear energy is cheap to produce, but the nuclear power plants are very, very, very costly to make. Secondly, nuclear energy does not contribute to greenhouse gases. That is the second advantage. But nuclear energy does have some emissions, but the plant itself does not give off any greenhouse gases. Studies have shown that what life cycle emissions that the plants give off are on par with renewable energy sources such as wind power. The WNA reviewed several studies and concluded greenhouse gas emissions of nuclear power plants are among the lowest of any electricity generation method on a life cycle basis are comparable to wind, hydroelectricity, and biomass. That shows how little carbon dioxide emissions, greenhouse gases that the nuclear power plants produce. However, nuclear fission chambers are cooled in boiling water reactors and pressurized water reactors. In pressurized water reactors, steam is produced indirectly by running cold water through primary pipes and secondary pipes. Remove the heat away. So the coolant is not in contact with the reactor. In boiling water reactor, steam is produced directly as the water runs through the reactor's core. So if there is any leakage of fuel, the water can get contaminated and is transported to the rest of the system. And nuclear energy is dangerous when leaked or contaminates other mediums, as pollutants released by the nuclear plants are heavy metals and toxic pollutants that harm plant and animal life in aquatic bodies. Water is released into the atmosphere after being cooled, but is still warm and damages the ecosystem of the sinks it flows into. Nuclear reactors are built with several safety systems designed to contain the radiation given off in the fission process. When these safety systems are properly installed and maintained, they function adequately. When they are not maintained, have structural flaws, and were improperly installed, a nuclear reactor could release harmful amounts of radiation into the environment during the process of regular use. If a containment field were to rupture suddenly, the resulting leak of radiation could be catastrophic. Alright, nuclear energy or electricity is made in a nuclear reactor. Nuclear reactor uses uranium, and uranium has three isotopes, which are uranium-234, uranium-235, and uranium-238. However, only uranium-235 can be used directly in production of nuclear energy. So, when the nuclear 235 splits, it produces like a immense amount of heat, and that heat is used to turn water, convert water into steam and used to turn the turbines to produce electricity. Basically, it does the same job as the coal, oil, and natural gas plants. And then uranium 235, like in the atoms, the nucleus is very unstable. So when the atom fissions, right, the nuclei breaks up and releases neutrons. These neutrons hit uranium atoms, which also split, triggering a chain reaction. And at that point, fission becomes self-sustaining. As uranium-235 is radioactive, the reaction is controlled by rods, which can slow down or accelerate the reaction. There's also another isotope, which is uranium-238. That uranium-238 cannot be like directly converted to like heat energy. But it will be it will be turned into plutonium, and the plutonium will, when it breaks up, it will only produce 1/3 of the reactor's energy output. Nuclear energy is one of the cleanest forms, and there are no carbon emissions, and water is recycled. As a result, it supplies about 11% of the world's electricity. Basically, this is what makes the nuclear energy very something that doesn't emit any carbon dioxide at all, because it only uses heat, and it doesn't produce any smoke or anything. It's just the only thing that's bad about it is that it's radioactive.
The current amount of energy usage by Singapore and the energy sources used to meet the demand. We don't have a lot on this because it's not information that's readily made available, so we took what we could. But the current amount of energy usage by Singapore is 47.69 billion kilowatts per hour annually. The energy source mainly used for Singapore's energy usage is natural gases, and about 95% of Singapore's electricity is currently generated using natural gas, compared to just 26% back in 2001, when Singapore preferred using oil as fuel instead of natural gases. As Singapore's energy market was liberalized, many power generation companies turned to more efficient gas turbines. And currently, the other 5% of energy generated comes from waste materials instead. Calculate and conclude the reliability and sustainability if nuclear energy was implemented in Singapore. Now, in 2012, a pre-feasibility study concluded that nuclear energy technology was unsuitable for use in Singapore. Locating a safe site for a power reactor was and continues to be a main concern, given that Singapore is a densely populated island state where any critical economic disruption would paralyze the country. As you can see in other countries like the US or Japan, where there are specific sites dedicated to these nuclear power plants, and there are fewer households and businesses that are running around those areas to prevent further damage. Now, in Singapore, where we don't have a lot of space and we're very cramped and overpopulated, we don't have that space, and so in case of anything, like in case of any disruptions to the power plant itself, it may take a large toll on our economy as well as our population. Now, going by Singapore's size, the global standard of an adequate safety radius between the reactor and the populace cannot be met. Economic activity is prohibited within this radius, and homes, businesses, and roads, if possible, cannot be built. Compared to the United States, where 1.3 square miles is the average amount of land needed for one nuclear plant, and in total to supply 1/3 of the energy needed by the US is 692 square miles. Singapore is only 278.6 square miles, and we already do not have space for more homes that are needed to be built, and thus to sustain a nuclear plant will be very hard, and nuclear energy technology is unsuitable for use in Singapore.